Hi everyone. We are going to start magnetic effect of electric current. That's our next chapter. Let us start with the introduction. So what is electromagnetism? So electromagnetism is a branch in which basically we deals with charges or electrons, motion of them in magnetic and electric field. And to be precise, if we are talking about electromagnetism, then in electric and magnetic field, how charges behaves, what is their motion, how they experience force, what happens if they experience force, right? And before we start this magnetism, there are two things which we are going to do. One is who is going to produce magnetic field. Second is who is going to experience magnetic field. So answer is same. It is basically a moving charge. So a moving charge inside a magnetic field experience a force, as well as it is a moving charge which produces the magnetic field, right? So magnetic field production is the first thing which we are going to study. So moving charge is nothing but current, right? So in current also, current carrying wire, if there is a current carrying wire, then there are electrons moving in that. So we will say that it is current or moving charge which produces the magnetic field. So for that, we are going to study the Biot-Savart's law. So Biot-Savart's law just tells us that if there is a current element, then how much magnetic field it produces. So Biot-Savart's law in equation describing the magnetic field generated by a constant electric current, right? And it relates the magnetic field to the magnitude, direction, length and proximity of electric current. Like if we have the current, then how much will be the magnetic field? Now this is the statement that Biot-Savart's law, it states that at any point P, the magnetic field dB, so due to an element dl, so this is an element dl, very small element, so very short length, there is the direction is same as the direction of current. So if in this wire the current is flowing in this direction, then dl will be taken like in this direction. So due to this dl element which is carrying current I, okay, the magnetic field is given by this. Now this is the directly a statement. So this is mu naught upon 4 pi I dl cross r cap. If you want, you can also go for dl cross r vector. But if you are using r vector over here, then it will become r cube, right? Because r cap is what? R cap is r vector by r. So there will be additional r. Now what is r? R is the position of the point at which we are going to find dB. Now what is this mu naught? First, mu naught. The mu naught is known as the permeability of the free space. Okay, permeability of the free space is mu naught and its value is basically 4 pi into 10 raised to power minus 7 Tesla meter per ampere. So the about units we are going to discuss when we learn more about magnetic field. So this is the value which you need to remember. Now one more thing, the direction of this magnetic field. Magnetic field is a vector quantity. As you can see, it is a cross product of two vector quantities. So to find the direction, you need to do direction is same as dl cross r vector. For direction, you can use r vector. R cap is same as this direction. So dl cross r vector will be using right hand rule to get the direction. Okay. First is SI unit. So magnetic field is represented by the letter B and its SI unit is Tesla. Okay. So magnetic field is measured in Tesla. Second is direction of magnetic field can be found by the rule of vector product. If you use dl cross r using right hand rule, then you can get the direction. Here I am giving you an example also. So they are saying that this is the direction of dl, right? So direction of current or dl is same. So take your right hand in the direction of dl, then turn it towards r vector or r cap, both is the same thing, and then your thumb will be showing the direction of d vector. Okay, db vector. Db vector is a very small magnetic field produced by this small element dl which is carrying I current at r vector position, like r position, right? So one more thing, the db is basically dl cross r. So the direction of magnetic field is perpendicular to this dl as well as this r vector. So dB is perpendicular to both of them since it is a cross product of these two quantities. Now there are some applications of Biot-Savart's law. So what we are going to do is we are going to utilize Biot-Savart's law and then we are going to find magnetic field due to various distributions, you can say various current distributions, various current carrying wires. Okay, so in first, that is magnetic field surrounding a thin current carrying conductor. So here we have a conductor. This is a piece of conductor carrying I current at a distance r at point P. We need to get the magnetic field produced by this finite piece of wire which is carrying I current and at a distance r. Now, if we join this point P to both of these ends, then the angle formed are theta 1 and theta 2. Let us derive it. Now, this is my piece of conductor. Now, it is carrying I current at a distance r I am talking about. This is angle theta 1, theta 2. So, first thing what I am doing is, I am going at a distance r. So, I am going at angle theta and then let us call it y, and then I am taking an angle of d theta. So, this is d theta. This is also almost y only, and then this distance is roughly r d theta, right? So, distance is y, so this will be y d theta. Next thing is, this distance over here is, let's say, x, and this element is having a width of dx. Now, due to this element, I am going to find the magnetic field at this point, which is P. And then I am going to integrate such pieces to get the entire magnetic field. Now, let us just look at the angles over here. So, this is theta. So, this is going to be how much? This is theta. This is 90. So, this is 90 minus theta. Let's just come to this small section. So, this angle, see, this angle is 90 minus theta, right? So, it was 90 minus theta over here. This is theta. This is 90 minus theta. This is again almost 90. Because this is d theta, which is almost 0. So, both of these angles are almost 90. So, this is 90. So, this is also 90. This is 90 minus theta. This is 90. So, this is going to be theta, right? So, now, what about this width? This width was dx. So, this is my dx. What about this? This was nothing but y d theta, right? So, this length is y d theta. Now, let us relate this. I will say dx is the diagonal. So, dx cos theta, because this angle is theta. So, dx cos theta, here I am writing that dx cos theta is nothing but y d theta. That's the first relationship between the dx and the d theta. So, that's the important thing. We'll keep it so that we can utilize it later. One more thing we will be using from this triangle. Okay, this triangle. I will say that it is y cos theta is r and y sin theta is x. So, I am simply using this right angle triangle. Here, this is right angle. So, I am saying y cos theta. That's my r, and y sin theta. That's my x. Two more relationship we got over here. One relationship we got here. Now, let us start. So, this dx, this is my small element carrying I current, right? So, this is I into dl. Instead of I into dl, we'll write I into dx because the element width is dx. Due to that, at r vector, and which we have taken as y. So, at y distance, here we have to get the point P, we have to get the magnetic field. So, using Biot-Savart's law, what do we write? We write that dB, the small magnetic field produced, is how much? Mu naught upon 4 pi I dl. What is dl? dl is dx in this case. Cross r cap. So, dl cross r is what? So, dl cross r is dl r sin theta, but r cap is unit vector. So, its magnitude is 1. So, I am simply writing that dx sin theta, where angle between this dx vector and this is the angle which I have to write. So, this is my theta. This is 90 minus, so this is theta. This is 90 minus theta. So, this is going to be 90 plus theta. So, angle between this dx vector and y vector, which is dl vector and r vector, right, is nothing but 90 plus theta. So, I'll write sine of 90 plus theta upon r square, which is y square in this case. This is my small magnetic field produced due to this. What about the direction? Direction is dl cross r. So, as you can see, it is into the plane. So, here it is into the plane due to any element. If you take this element, dl is always above, r is always that way. So, it is, my thumb is into the screen, right? So, it is always into the plane. And now, I can simply integrate it to get the total magnetic field. So I'll say total magnetic field is nothing but integration of this. Now in this we'll put some quantities. First it is integration mu naught upon 4 pi, that's a constant. Now I is also constant. What about dx? Remember the dx we got here. The dx is nothing but y d theta by cos theta, right? Or dx cos theta we can directly write as y d theta. If you come over here, so this is my dx and this is what? Sin 90 plus theta is cos theta. So this is dx cos theta. So entire thing is y d theta upon, what about this? This is y square. I'm not writing y in terms of theta as of now. I will cancel one of the y. And now in this expression I have d theta. And y is still a variable, right? Y will change. For this it will be something, for this it will be something. So I'm using the relationship which I found over here. So I need the relationship between y and theta. So if I use this, I get another variable. So I'm going to utilize this. So I'm going to write y as r by cos theta. R is a constant. R is this fixed distance, right? So y is nothing but r by cos theta. Let's put y as r by cos theta. It's integration mu naught upon 4 pi I d theta and upon y. Y is nothing but r by cos theta. So cos theta goes over here. And now that's my expression. All the things are constant except theta, right? So now I'll write constant will come out. They will remain as it is in the process of integration. So mu naught upon 4 pi I by r, and it is integration of cos theta d theta. Now it is the time to put the limit on what? Theta. So come to this figure again. Now we are saying that we went to theta and took an side of d theta, right? So our theta is varying from what? It is varying from minus, see, angle is again in a particular direction we are going. So this is other way around, it will be minus theta 2. So angle is changing from minus theta 2 to all the way minus theta 2 to all the way up to plus theta 1. So I am putting my limit from minus theta 2 to all the way up to plus theta 1. Once I integrate, I'll get my expression for magnetic field. What about the direction? Direction at point P is into the plane of the paper, which we will learn another rule. So again, I am writing mu naught upon 4 pi I by r. What about the integration of cos theta? It is sin theta. So sin theta, limit is minus theta 2 to positive theta 1. And now put the limit mu naught upon 4 pi I by r, and in bracket we get sin theta 1 minus sine of minus theta 2. Now what is sine of minus theta? It is minus sine theta. So this is our final expression, that it is mu naught upon 4 pi I by r. R is the distance, I is the current in the wire, mu naught upon 4 pi is the constant. And then we have sine theta 1, then this becomes minus sine theta 2. So minus of minus sine theta 2 is plus sine theta 2. And that's an expression for the magnetic field due to a, so this is just the magnitude. Direction we can get using the right hand rule, right? The vector product rule. So this is the magnitude mu naught I by 4 pi r sin theta 1 plus sin theta 2. What is theta 1 and theta 2 again? When you join the point where you have to get the magnetic field to both the ends of the wire, the angle formed are theta 1 and theta 2. You can take them other way around also, as there is a symmetry. There was sin theta 1 plus sin theta 2. Now, this is the formula which we had derived, that it is mu naught I by 4 pi a. The distance they have taken is a, right? Sin theta 1 plus sin theta 2. Now, let's move to some special cases about this particular magnetic field due to a piece of current carrying wire. Now, for a conductor of infinite length, first case is, what if our length is infinite? So, we will say that if length is infinite, then we will be saying that in this, the theta 1 and theta 2 both will become how much? Both will become, see, when this goes to infinity and this also goes to infinity. So what about theta 1? Theta 1, this point will be almost going like this till infinity. So this theta 1 will become 90 degree, right? It is almost 90 degree, so it will never meet. It will become parallel, and theta 2 is also 90 degree. So we put both our theta 1 and theta 2, as 90 degree in this expression. So I'm putting my theta 1 as theta 2 as 90 degree, and sine 90 plus sine 90 is 1 plus 1. So this is 2, and eventually we get mu naught I by 2 pi r. That's an expression for r is the distance. So mu naught I by 2 pi r. R is the distance at which we have to get the magnetic field due to a finite wire, right? Infinite wire. So this is the magnetic field due to a infinite wire. Next case is magnetic field at a point on the line of the current. So line of the current means this is our wire which is carrying some current, and now let us say we have to get the magnetic field either here or here. So this is my DL, right? So if I join this, like see, let's say the wire is only this much. You join this point to here, the angle is going to be how much? See, if the point was here, then this was the angle. But if this point is here, angle is almost either 0 or 180 degree, right? So these 2 points, the angle will either be 0 or 180 degree, like you join this point to here and the middle, right? So angle is going to be 0 or 180 degree in both the cases. If we take the point over here, then also it is going to be 0. So theta 1 as well as our theta 2, both are going to be 0 or 180 degree at both. Sin theta value is 0. So this is 0 and 0. So overall, the magnetic field is 0. Again, if this is a wire, then we are talking about some point here or here on the length of the wire or on the axis of the wire itself. Then the magnetic field produced is 0. We'll be using this in a lot of questions, okay? Now, so if a point lies on the line of the current carrying wire, with then magnetic field at this point is always 0. Like the current does not produce any magnetic field in this line, okay? Next case is at a point exactly in front of one end of a semi-infinite wire. So here we have a semi-infinite wire. Wire is basically infinitely long this way, and it is carrying I current. This is like wire is infinite other way, and now I am taking a magnetic field at point P. So I'll say that join this point to both the ends. One end is here only. So my theta 1 is that way, right? So theta 1 is nothing but 0. What about theta 2? You join this point to other end, and other end is infinite. So this line will go almost like this. So this theta 2 is nothing but pi by 2. So just put theta 1 as 0 and theta 2 as pi by 2 in our formula. So if this is 0 and this is pi by 2, then we get one thing is 0 and one thing is 1. So we'll get mu naught I by 4 pi r or 4 pi a, right? So r is nothing but this perpendicular distance is my r or a. So this is the magnetic field due to infinite, semi-infinite wire, we can say like that. We are saying that it is infinitely long but just one-sided. We are at the other end. Now there is a question. So let us discuss this question. This question says an electric current passes through a long straight wire. At a distance 5 cm from the wire, the magnetic field is B. And now they are saying find the field at a distance 20 cm from the wire. So what will be magnetic field? So we already know that B is what? B is, see, they have not given, it is long straight wire. Whenever long straight wire written, we take it as infinite wire. So we know the formula that it is mu naught I by 2 pi r. I am not going to utilize the whole formula. I know that B is proportional to what? B is proportional to 1 by r. So I can just write that B1 by B2 is nothing but it is my R2 by R1 because it is inversely proportional. In case number 1, the magnetic field is B when the distance is 5 cm. In case number 2, we have to get the magnetic field when the distance is 20 cm. So it is 5 4s, and once we solve, we get the X is equal to the required magnetic field at 20 cm distance as B by 4. And since it is inversely proportional, you are making the distance 4 times. So B will be reduced by 4 times, and hence B is the correct option. This is our next question. It says that two infinitely long wires carrying current I, they are bent as shown in the figure. This is infinitely long wire and bent like this, and this is another infinitely long wire bent like that, right? As shown in the figure, and they are saying find the magnetic field or magnetic induction at point C. So this is the point at which we have to get the magnetic field. Now first is I'm dividing those wires, like this is one wire, this is another wire, in 4 parts. One part is this infinite long wire, or to be precise, semi-infinite long wire. Now due to this, the current is coming like this and point C is on the line of wire, so this will not contribute in the magnetic field at all. Second is this wire. Now current is going away from C, so again this is lying on the line, so due to this semi-infinite also, it will not contribute anything at all in the magnetic field. Now there are only these 2 parts left. Now this is a semi-infinite long wire. Due to semi-infinite long wire, it is mu naught I by 4 pi r, right? So I am writing that due to this it is mu naught I by 4 pi r, and due to this also mu naught I by 4 pi r. But the trick is the direction, because both the things are vector quantity, we need to add them very properly. Now due to this I, see, this is the direction of the current, R is that way, so I am just coming this side, so it is basically dl cross R, so it is outside, right? Or there is other ways, you grip the wire. So at this point, it is basically out of the plane due to this. The magnetic field is out of the plane. Due to this, again, just do dl cross R, so L cross R, so out of the plane. Sorry, both is out of the plane only. So this is out of the plane, this is also out of the plane, so both are in the same direction, we can simply add it. So I'll say the total magnetic field is basically mu naught, current is I in both the cases, by 4 pi r, and distance is a in both the cases, and it will simply be this plus same thing, so I'm saying into 2. So magnetic field comes to be mu naught I by 2 pi a. So that's magnetic field induction at point C, direction is out of the plane of the screen. Okay,